In today's video, we will be talking about how to graph rational functions. In previous videos, we've been focusing on polynomial functions, which had very nice properties like continuity, from the left to the right forever. But today we introduce a topic that you may remember from your past, maybe not so fondly, rational functions. Let's get started. We begin in this example with a graph that's been provided to you, and it says, can you analyze this graph of the given rational function? Now, one of the reasons that a student should be able to recognize this as a rational function is because we recognize that the graph breaks into different pieces. At certain x values, the graph is no longer defined. So if I were to superimpose a dotted line wherever the graph has broken apart, apparently, then I would see that apparently it looks like at x equals, let's see, 1, 2, 3, 4, 5. So at x equals -2, let me grab my pen here with maybe a brown color. It looks like at x equals -2, the graph has broken apart. And if you remember from your previous lessons on rational functions in your past and other courses, that would be called a vertical asymptote. We'll be talking more about how to find those ourselves when given the equation later today, at x equals -2. And there's one other location in this graph that we can see a break happening. And that looks like x equals, yes, +2. Good job. So at x equals +2, I'll put in another vertical asymptote. Again, that represents a place in the graph where there are no legal inputs, no legal x values, because such values would make 0 in our denominator, which is undefined. So one of the things that we need to get used to, if we're not already familiar with it, is the concept of limit notation. So if we notice here, we have this graph and we have 3 pieces of it, but we're asking very specific questions about approaching different x values. So let's take a look at the first one. It says, as x, and we read that arrow as approaches, as x approaches -2. Now the superscript, the plus sign above and to the right of the 2 there, it's a direction. So it's telling me the direction that I'm coming from as I approach this number. If it's a plus sign up there, we think from the right. So let me write that for you. From the right. That's what that plus sign. And if it had been a minus sign, it would mean from the left. That's right. So in this situation, we're going to say, as x approaches -2 from the right, f of x approaches what? Well, let's take a look. At -2, that's our vertical asymptote here, the first break in the graph that we see. And we're supposed to be answering the question, where is our function, our y value, our f of x, where is it approaching as x approaches -2 from the right? So let me grab another color perhaps. Let's see, blue. As x approaches -2 from the right, that would be this piece here. We would notice that our growth is approaching up, the up direction. In other words, as x approaches -2 from the right, f of x, our function's output or y values, are getting bigger and bigger, meaning they are approaching positive infinity. That's right. Good job. See if you can answer the next one on your own. Feel free to pause me. All right, so the next one says, as x approaches -2 from the left, f of x approaches what? Let's take a look. Again, -2 is this vertical asymptote. And we're asking, what would our function's output be approaching as x approaches that vertical asymptote, -2, from the left? So from the left. Well, from the left, wouldn't that be this piece? So what are my outputs approaching? Not a single number, but rather a direction. They're going down. They're getting lower and lower and lower and lower, meaning they're approaching -infinity. That's right. So if that's what you said, good job. Again, feel free to pause the video and see how much of these you can do on your own. All right. As x approaches 2 from the right, f of x approaches what? Well, 2 would be this vertical asymptote. Okay. So from the right, yes, that's right. That would be this direction. So we would have our graph going down forever. So again, it would be approaching y values of -infinity. And finally, as x approaches 2 from the left, that would be this piece. Good job. our y values, our f of x, our function outputs, are getting bigger and bigger, meaning they are approaching positive infinity. Okay, so getting used to limit notation definitely takes practice, and make sure you take advantage of the homework in the book and online to make sure you really feel comfortable with that. But some things that should be more familiar to you already are things like domain. So let's take a look at our domain here for this situation. The domain, again, is a set of all possible x values, or inputs. Well, there's only two problematic inputs in this graph, and that is where we have our breaks in the graph, our vertical asymptotes. So we know that x cannot be -2 or +2. Both of those would create problems in our denominators, making the graph break apart there. So if we want to exclude on a number line, for example, -2 and +2, what we're really saying is that any value to the left of -2 is okay, any value in between -2 and 2 is okay, and any value to the right of 2 is okay. But at -2 itself and at +2 itself, we have no existence there because they create zeros in our denominator, making the graph break apart. So to write this out in interval notation, we could say -infinity until -2. That says values which are smaller than -2 are allowed. Union, which means or. Values between -2 and 2, so parentheses -2, 2, union or. Values to the right of 2, so parentheses 2, infinity, close parentheses. So that would be our domain for this rational function. Now, if you remember from our previous videos where we were graphing only polynomial functions, there were no holes, there were no vertical asymptotes because our graphs were continuous everywhere from left to right forever. So our domain in those cases was always -infinity to +infinity. So none of these restrictions were necessary. But because rational functions have denominators, we do have those situations where sometimes we have problematic values for x in the denominator. Finally, the last question on this example was, does this graph appear to have symmetry? And in previous videos or lessons, you've learned about symmetry. We had y-axis symmetry, where we have a mirror image along the y-axis. We had origin symmetry from quadrant 1 into quadrant 3, or quadrant 2 into quadrant 4. And this one almost appears to have symmetry of perhaps y-axis type. But the problem with that, if you take a look at the graph carefully, is that over here, around a value to the right of 1 for x, we have a y value which is nice and low, below 1 for y. But on the other hand, that same value on the other side is up here, above 1. So you can see that those are not quite symmetrical on the y-axis. We also note that there's no origin symmetry from quadrant 1 into 3 or 2 into 4. So we would say this graph appears to have no symmetry. Okay. So that's an example that we've done now where we've given you a graph and you've analyzed it. You've talked about the limit notation as you approach your asymptotes, what's happening. You've talked about the domain, and you've even reminded yourself of the symmetry. But what about when we give you an equation? How would you even begin to draw the graph of a rational function? Let's review some of the main things that we have to know about. We need asymptotes. We can see that the vertical asymptotes are important here. But it turns out there was another type of asymptote that you might not remember, and that was our horizontal asymptote. So the horizontal or the slant asymptote was also an important asymptote that we needed for our graph to get a complete sketch. And then intercepts and symmetry are also helpful. So let's remind ourselves of how to get those asymptotes on our next slide. So to find asymptotes, we start off with looking at the vertical asymptotes, remembering that sometimes your numerator and your denominator, like we have here in our box, will be expanded out, and we'll have to first factor. Now, once you've factored, there could be the case, let me switch colors so you can actually see me, here we go. Once you've factored, it could be the case that you actually can cancel some of those factors. And if you remember when you first studied these types of functions in your past, whenever you canceled factors, that's when we produce something called a hole in the graph. So instead of a break in the graph like we saw in the last example, we would just have a little hole where there's an x value that can never be reached, but the y values above and below it are okay, just not at that location. So we'll talk more about holes in our examples later today. So if our factors cancel in the top and the bottom, that's when the hole occurs at that problematic x value. On the other hand, if there are any denominator factors which do not cancel, then we can set those factors equal to 0 and then solve to find our vertical asymptotes. In our next example, we'll practice doing just that. Similarly, we need to talk about horizontal or slant asymptotes. And those were found, if you remember from your previous courses, by comparing the degrees of your numerators and your denominators. So if you're in expanded form on top and bottom, you would just look at the highest power. If you were in factored form on the top and on the bottom, you would have to first add up those multiplicities, those powers, to figure out your degrees for the comparison. In the box below, we see the summarization, or the summary rather, of those three types of situations that could happen. Remember that if the degree of the numerator, which we're calling n here, is less than the degree of the denominator, that meant that we did have a horizontal asymptote at y equals 0. And if the degrees were equal, then we did have a horizontal asymptote, and we got it by taking the ratio of our leading coefficients. And finally, remember that if the degree of the numerator was greater than the degree of the denominator, then in that situation we had no horizontal asymptote. But there could have been potentially a slant asymptote. So at the bottom here, if you can't see it because I planned poorly for that part, sorry. The third part there was that if the degree of the numerator was larger than the degree of the denominator, then there was no horizontal asymptote, but maybe a slant asymptote. Now, what a slant asymptote does is instead of approaching a single y value as we go left and right forever, we approach a line, and it's a slanted line with a certain slope. And so to find out what the slant asymptote is, our third bullet point here says, when no horizontal asymptote exists, if the degrees are exactly 1 apart, if that's the case, then in that situation we could use long division. We could use long division to find any slanted asymptotes. Okay, so I will be going through the reasoning for these rules again as we get into our examples, but it's a good place to have a summary of those rules, and so that's what I've put on this slide for you, a nice summary of everything. So let's get started applying the rules and seeing why those rules make sense if you've never seen that before. This might be interesting. So here's our first example, and it asks you in example 2 technically to find any vertical asymptotes, holes, and state the domain of the function. Here it tells me that f of x equals x squared minus 4 over x cubed minus 4x. Okay, so to get started, what I would want to do is factor. Great job. So let's take a look at the factorization here. The numerator is a difference of squares, so that would become x plus 2 times x minus 2. In the denominator, make sure you recognize that there is a greatest common factor of x. So if I factored out the GCF there, I would have x squared minus 4. But technically, we just did that a second ago, didn't we? In the numerator, we did. So let's replace that with what we know it factors into. So it factors nicely into x plus 2, x minus 2. Now the reason I did that is I can now see the 3 problem areas for x, but I'm going to be able to cancel as well. So let's talk domain first. If I was interested in the domain, I would notice here that there is some cancellation that's going to happen, but before I do, the 3 problematic factors would be if x was 0, so x cannot equal 0, if x plus 2 equaled 0, so that can't happen, otherwise the denominator would turn 0, or if x minus 2 equaled 0, so that can't happen, otherwise we'd have an undefined fraction, wouldn't we? So it turns out that x can't be 0. Solving for x in each case then, x can't be, that's right, negative 2, and x can't be positive 2. Well done. Putting those 3 together in interval notation, what we're saying again on the number line is that negative 2 is excluded, 0 is excluded, and 2 is excluded, but anything else is okay. So interpreting that, let's see, with this color perhaps, any value to the left of negative 2 is fair game, but not negative 2 itself. Any value between negative 2 and 0 is fair game, but not 0 itself. Any value between 0 and 2 is fair game, but not 2 itself. And any value to the right of 2, but not 2 itself. Meaning, if I were to summarize that, my domain would be negative infinity until negative 2, union, negative 2 to 0, union. What else? 0 to 2. Yep, good job. Can you get the last one? Union. I'll have to make some space for us. Okay, what would the last one be? That's right, 2 to infinity. Sorry, multicolor there. Okay, so there would be our 4 regions of the domain, which are appropriate input values for x. Values left of negative 2, in between negative 2 and 0, in between 0 and 2, and values to the right of 2. Okay, but at those values 0, negative 2, and 2, we would have a 0 in our original denominators. Okay. Now, once we found the domain, it's now safe to talk about which of those problematic x values, inputs, right, which of those would have produced vertical asymptotes, and which of those would have produced holes, because there is a distinction in the graph. In the hole, we just have one little location where we have to jump over that point. But in the vertical asymptote, there is a massive break in our graph. So that's the difference there. One is removable and one is not. So taking a look at my original function, that rational function in factored form, what cancels? That's right, x plus 2 and x minus 2. Death to you, death to you. So what's remaining? Just 1 over x. So it turns out that our original function is really the graph 1 over x. That's interesting. Who would have thought, right? And that's technically a graph that we have studied before. You might remember it. It has nice origin symmetry with a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. That was called our reciprocal function that we would have studied in previous courses. Now this one is special though because it has a hole. It has actually 2 holes. What are those holes? Well, the holes would be coming from the factors that we've canceled. So the denominators that got canceled were x plus 2 and x minus 2. Setting those equal to 0, we get our problematic spots, which are negative 2 and positive 2. So we know that at x equals negative 2 and at x equals positive 2, we have our holes. If we wanted to know what the holes themselves are, we would need a coordinate, wouldn't we? So we would need the x value at negative 2 and the x value positive 2. But how would we find the y value? Well, let's think. If we plugged in those values into the original function, we have a problem immediately at those denominators, those factors rather, of x plus 2 and x minus 2. On the other hand, couldn't we plug them in, the x values, into the reduced version and have no problems? Yeah, and that's what we'll do. Let's plug in the x value negative 2, and we would have 1 over negative 2, which is just negative 1/2. And we would have 1 over 2, which is just half. So now we found the 2 locations where we have a hole. So we would literally be traveling, we'll hit the hole, we'll skip that point, and then we'll continue on our way. That's what a hole means, okay? Also known as a removable discontinuity. But the vertical asymptote, there is still a vertical asymptote, and we can see that from the sketch of 1 over x directly. The vertical asymptote is at x equals 0 for this reduced function. But we could also see that because that's the surviving factor in the denominator after cancellation. So you take your surviving factors in your denominator and say they still can never equal 0, meaning x equals 0 is the location of my one and only vertical asymptote. And that's what's happening in that picture there. Okay, so again, to recap, to find vertical asymptotes or holes, we first factor our numerator and our denominator, see if anything can cancel, and if they do, that's a hole. If they don't, that's a vertical asymptote. And remember that the domain takes into account both holes and vertical asymptotes for restricting our inputs, our x values. Good job. Let's get started with another example, but with horizontal asymptotes this time. In example 3, it says, can you find any horizontal or slant asymptotes for the rational function, if possible? Again, remember our 3-step rule? Sometimes there are no horizontal asymptotes and there are no slants. So it is sometimes going to be that case, okay? The if possible situation. Okay, so let's get started with our first one. It says f of x equals 2x squared plus 1 all divided by x. So in that situation, I can see, well, does anything factor? And no, nothing does. But I'm not looking for a vertical asymptote, which would have been 0, by the way, by letting x equal 0. But instead, I'm looking at horizontal or slant asymptotes. And to do that, I compare the degrees. The degree of the numerator is 2, our highest power here. And the degree of the denominator is, that's right, it's implied to be 1. So since the degree of the numerator is greater than the degree of our denominator, that's the situation where as x approaches positive infinity, as x gets really, really big, which of them is growing faster, the numerator or the denominator? That's right, the numerator, which means that there's nothing to stop this growth. This is going to continue to grow. It's not going to approach a single number for y. So there is no horizontal asymptote. And we can look back at our rules and see if this rings a bell. Let's go back a couple slides, see if we see that. That's this situation at the very bottom, which was hard to read, but that's a situation where there was no horizontal asymptote. Okay, so let's head back to where we were here, and let's get rid of that part there now. Okay, so we now know that there is no, oops, that's not the pen. Sorry about that, I'll fix it. There is no horizontal asymptote because the degree of the numerator was greater than the degree of the denominator. Now, if you're curious about why this is the way it is, I will tell you a little trick here. This is how a calculus student would typically approach this problem. Instead of thinking about memorizing one of those 3 rules, what they would have done is said, well, here's what I know is happening. As x gets really, really large or really, really small, we're looking to see whether or not our function is approaching a single number, a y value. And so what you would do is you would divide every term by x to your highest power. That sounds kind of strange, but let me show you what I mean. So that would be your first step. So if you had, for example, 2x squared plus 1 in your numerator, and in your denominator, you just had x. You can take, maybe, let's take white here. You would say, let's divide every term by x to the highest power. Well, x to the highest power was x squared, wasn't it? So I'm going to divide every term by x squared. Now, you might think that's really strange. Why are you doing this to me? I'd rather just memorize my rule. Feel free. You're welcome to just memorize a rule and know the answer is no horizontal asymptote because the degree of the numerator was higher than the denominator. However, I think that if you understand where this rule is coming from, you're much better off, especially if you're going on in math. Because what's happening here is if you do this trick, you basically are just multiplying the top and the bottom by x squared, which is in the end dividing both of them by x squared at the same time. That's 1, so it's perfectly legal. But why we're doing this is that now we can see some things cancel. X squareds cancel there. And down here, this becomes 1 over x, right, instead. Now, why is that nice? Because what we're really doing with a horizontal asymptote, if we have one, is we're saying what is happening as x gets really, really large, or as x gets really, really small. So in other words, we're saying, is there a limit? We'll use this notation a lot in calculus. As x gets really large, as x approaches infinity. Well, let's think this one through. Right now, we just have the number 2 here, so there's nothing that can limit a 2. It's always going to be a 2. But what about if I have 1 over something really, really, really large that's getting squared? For example, 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000,000. That's getting smaller and smaller, that fraction. In other words, that fraction, I'll use this arrow to mean approaches, that fraction would approach, that's right, 0. So the numerator would approach 2 plus 0, or 2. But in the denominator, what would have happened is if you replaced x with infinity, as x gets really, really large, we would get 1 over infinity, which means that whole fraction is also approaching 0. But notice that can't happen. This is saying that we would have 2 over 0 that we'd be approaching. But this is undefined, which means it's telling us something. It's telling us there is no limit. No such limit exists, which means there is no horizontal asymptote. So that's the reasoning behind that third rule. All of the rules work the same way. if you do it the same way that I just mentioned, this trick here, divide every term by x to your highest power, and then take the limit as x gets really, really large, what will happen is you'll get one of those three rules that pops right up in front of you. So rather than memorizing them, if you understand the process of what an asymptote is, a horizontal asymptote, you're much better off in the future. Okay, well, I'm going to erase that part, but feel free to pause it if you want to take a look at it some more. Let's get a big eraser and move on here. Okay. What we're going to do next is we're going to talk about slant asymptotes and when they would exist. It turns out that for this problem, we might have a slant asymptote. If you go back to your three rules from 2 slides ago, we talked about the fact that when there is no horizontal asymptote, there could be a slant asymptote. So we have to ask ourselves, is there a slant asymptote here? And in this case, the way we'll know that is by looking at the degrees again and asking ourselves if they're exactly 1 apart. 2 and 1, yep, they are exactly 1 apart, which means yes, there is a slant asymptote, and that's because if I were to divide a degree 2 polynomial by a degree 1 polynomial, I would get a degree 1 polynomial, also known as a line. So I would get a slanted line that we are approaching as x gets large and as x gets small. So the step that we need to follow now would be long division. But I promise it won't be terrible, it'll be a short little process. Let's take a look. So we would take our x term and divide it into 2x squared plus 1. And as I've mentioned in previous videos when we did long division, if you do long division differently according to where you grew up, feel free to do it that way. This is just the American way of doing long division, okay? So let's take a look at what this would be. We would say x times what would give me the leading coefficient, 2x squared. Yep, that's right, it would be 2x. So I'm going to put that maybe right here. You're always welcome to use a placeholder like 0x for the missing term. Then we would multiply, that's the next step in the algorithm. 2x times x is 2x squared. And next we would subtract, which means draw your line and change every sign. So when I do that, the first term should cancel. 0x is irrelevant to us here, but we can copy it if you like. And then the plus 1 would come down as well. So what's interesting here is that if we were to say x times what gives me 0x, that would just be plus 0. And that looks a little bit tacky. So normally we wouldn't write that, but if you want to, feel free. You'll end up getting your 0x plus 0 here. So you do get a remainder. You see that okay? Yeah, a little bit. You do get a remainder here of 1, but I wanted to make a note that when you're on the hunt for a slant asymptote, which is also known as an oblique asymptote in some textbooks, whenever you get that remainder, it's actually not important to keep it, because what you would normally say is, I put the remainder over the divisor here. But again, the idea here is what is happening as x gets really, really large. And if that's what we're talking about, then as x gets really, really large, 1 over a really large number really approaches 0. So the remainders are meaningless in this situation, in this context. So you can ignore your remainder on the hunt for a slant asymptote. We've now actually found the slant asymptote. You might have gotten lost in the details, but the goal was to find a slanted line that we're approaching as x gets large or small. And so our slant asymptote would simply be, I'll switch colors on you so it might be clearer. Y equals, again, a line is typically written in slope-intercept form, mx plus b. So our slope is 2x, and our y-intercept is 0, which you could write, but it looks tacky. So most of us would just write y equals 2x instead of y equals 2x plus 0. And you can check the Desmos link on the slide and see that that is in fact going to be the line that your graph will approach as you go to the right forever and to the left forever. So it's really nice when you put it all together. Okay, so we've done one example where there was no horizontal asymptote and a slant, okay? But what about the case in part B? In part B, we see h of x equals 2x minus 1 over x squared minus 5. All right. Now, if you looked and see, if you're looking for any vertical asymptotes, I should say, you would begin by trying to factor and set the denominator equal to 0. But if you're looking for a horizontal or slant asymptote, you're just comparing the degrees. So looking at the degree 1 for our numerator and 2 for our denominator, because the degree of the numerator is 1 and the degree of our denominator is 2, the degree of the numerator is less than the degree of the denominator. And again, you're welcome to try the trick that we did earlier. You're welcome to back up the video and watch that trick go down. This time, again, you would divide every term by x squared and eventually see that there is a horizontal asymptote. There is a limit as x gets really, really large or small. And that limit would be y equals 0. This is also the first rule from our previous slide. Let me just roll back a couple pages ago. Oh, that's a lot to see. But it was that first rule here that if the degree of the numerator was smaller than the degree of the denominator, I think I said that backwards, but you see it, it's a, then we do have a horizontal asymptote at y equals 0. Okay, all that writing, sorry. Okay, so we do know we have a horizontal asymptote. Now there is one thing I don't think I've mentioned today, but I do want to make that clear, and that is that a horizontal asymptote and a slant asymptote are what we call mutually exclusive, meaning they're disjoint. They cannot happen at the same time. So as soon as you have a horizontal asymptote, you can say, I know that there is no slant asymptote, and vice versa. Okay. Well, let's go on the hunt now for putting this all together. We've talked about vertical asymptotes, we've talked about horizontal and slant asymptotes. Can we put this information together to draw our own graphs of rational functions? Let's see what happens. We summarize here the main steps. If you were trying to draw the graph, for example, of f of x equals x plus 3 over x plus 2. I would notice this is not a polynomial function that we've been studying in the past because we have a denominator. This is called a rational function for that reason. So the first thing that I would want to do is get my intercepts, my asymptotes, and then some test points. That's basically the idea here. So for intercepts, some points that are guaranteed to be on the graph on the x or the y axis, I could begin getting my intercepts. By letting, let's say, x equals 0, because that would get me my y-intercept. So let's do that, f of 0, and see what we get. If you plug in 0 for x, that would be 0 plus 3 in the numerator, which is just 3, and 0 plus 2 in the denominator, which is just 2, or 1.5 if you prefer the decimal. So this would be my y-intercept, because that's when x equals 0. So I could go now to my graph, and at y equals 1.5, so up 1, up 2, right in the middle there. That's the location potentially of my y-intercept. What about my x-intercept? Well, that's when we would let, that's right, y equals 0. But isn't the entire function's output our y value? It is. So that means we would need to set the entire fraction equal to 0. But let's think about that for a moment. You're welcome to write it out and cross multiply and go through all that work, but thinking about it might save you a second. If you have a fraction, something divided by something, and it equals 0, what's the only way that that makes sense? Is the numerator 0 or is the denominator 0? That's right. The numerator has to be 0 because if the denominator were 0, it can't even be happening. It would be undefined. So really, to find my x-intercepts, I just need to set my numerator equal to 0 because that will make the whole output 0. So that would mean that x plus 3 would equal 0, but we know what that means. X equals negative 3. Good job. So 1, 2, 3, there's my location of my x-intercept, and at 1.5 was the location of my y-intercept. So we already have part of the graph pretty clear, I hope. But let's continue talking about vertical asymptotes and slant asymptotes, or horizontal asymptotes. So let's see here. If I was looking for a vertical asymptote, or a hole, I would start off by saying if I could factor anything, right? And in this case, x plus 3, x plus 2, there are no further factors. They're both already linear, aren't they? Be careful. Some students make the mistake of trying to cancel the x's down through the plus sign or the minus sign. Can't do that. Only factors can be canceled that are multiplied together on top and bottom. So x plus 3 and x plus 2 cannot be canceled, so there are no holes. Good job. But are there any vertical asymptotes? That's our next question, right? Well, yes, because there's one problematic x value that would make our denominator equal 0. And that would be when x plus 2 equals 0, or when x equals, that's right, negative 2. So that's the location of my vertical asymptote. Let me pick another color here. Let's try that. So at negative 2, that's where we have our break in the graph, our vertical asymptote. Okay, what about our horizontal or slant asymptotes? How do we talk about those? Horizontal asymptote or slant asymptote? Well, that was when we compared the degrees, right? Here the degree of our numerator is a 1, and the same is true for our denominator. So when the degrees were the same, that was actually the second case in our three-step potential situation with horizontal asymptote check. So we would know that's the case where we do have a horizontal asymptote and y equals the ratio of the leading coefficients. Here the leading coefficient happens to be a 1 in both cases, but those can depend on the actual problem. So make sure you don't assume it's always 1. It's going to be the ratio, the fraction of your leading coefficients. In this case, 1 over 1, which is just 1. So in this situation, we do have a certain y value, a single y value, that we should approach as x gets really big or really small. So let's draw that line, maybe a dotted line at y equals 1. So there's our horizontal asymptote at y equals 1. Now technically I claim that I have enough information to draw this picture. I have enough information to draw this picture. I just saw a mistake. I apologize. Maybe you caught me already. If so, good job. I said that the y-intercept was -3, but where did I put it? I put it at +3. That's a mistake. So let's put it in the right place. -3 would actually be 1, 2, 3 over here. That's better. I was getting concerned about my picture. And maybe you can see why I was getting concerned. It wouldn't make sense. Okay, so now that I have a better idea of my intercepts correctly on the graph, my asymptotes correctly on the graph, the question is, how much further do I have to go before I can simply draw a sketch, connecting the dots, if you will? Well, it turns out you should have enough at this point because to the left and to the right of your vertical asymptote, right here, to the left and to the right of it, you divided the graph into two regions, right? And because a graph of a function has to pass the vertical line test, every input produces only one output, we know that if we are down here, for example, you can see that, then we couldn't also be up here at the same time because that would no longer be a function. So if I am guaranteed an x-intercept below the horizontal asymptote, then I know this graph looks something like this. So as x gets further and further negative, it will approach the y value of 1. It will approach y equals 1, my horizontal asymptote. Interesting. Similarly, as x gets really large, it should also approach the y values of +1. So in the other case, our graph could either be up here, approaching 1 as we go to the right forever, or down here, approaching 1 as we go to the right forever. Now notice that it can't be the latter. It can't be down here for a couple of reasons. One reason is we have a point above, meaning it's probably up here. So it's probably looking something like this, right? Another reason, though, besides the y-intercept being above that line, we also know that the only x-intercept was at x equals -3. Once I drew it correctly, it was over here, meaning there can be no other x-intercepts on this side on the right of that asymptote. So the graph could not be down here. There is no way. If you want to make extra sure that your graph is in the right location, you could always use what we call test points by picking an input, an x value, any x value that you like in a certain region, plugging it into your function for x, and seeing what y value you get. That'll give you a better picture for sure. But this is a sketch. You've shown me the intercepts, you've shown me the asymptotes, and you've correctly interpreted what that means for each piece of the graph. Okay, let's try a harder one, and we're wrapping it up, I promise. Here we go. Okay, example 4. I think, yeah, this is our last one. Okay, whew, it's been a long lecture for you. All right, so let's get started. Feel free to pause this and work on your own first, but I'm going to get started now. Sketch the graph of f of x equals x minus 1 over x squared minus x minus 2. So what I notice here is that I could first begin by factoring. So my numerator is x minus 1, can't change that. But this denominator can factor, can't it? That's right, into two linear factors multiplied together, where they each start off with an x term, but their second terms must multiply to give me -2, but add up to give me -1, right? Multiply to give me -2, add up to give me -1. So that would mean maybe x minus 2 and x plus 1. And you can check that, right, by multiplying it out, seeing if you get back to where you started. Okay. Now you might be wondering, oh man, I thought we were going to have a hole. What happened here? You're right if you were thinking that. We almost did have a hole. Because if these signs had been the same in the middle, then those factors would have been identical and they could have produced a hole by cancellation. But because nothing cancels, we know that there are no holes, okay, in this particular function's graph. that means that we do still have potential for vertical asymptotes. In fact, I claim that we have 2 vertical asymptotes. Because if I were to set each denominator equal to 0, what would they be? That's right, x equals positive 2 and x equals negative 1. Well done. If you're wondering why did the signs change, that's because you've set them equal to 0, right? And you said what values for x would make that happen. Okay, so at x equals 2, we have a break in the graph. Let me make sure I put it in the right spot this time. There's x equals 2. That's one of my vertical asymptotes. And another one at negative 1. Okay, now that I have those vertical asymptotes on my graph, I can now ask myself about horizontal or slant asymptotes. Well, for a horizontal or a slant asymptote, we compare the degrees. So the degree of the numerator is a 1, and the degree of the denominator, 1 plus 1 is 2. You could have also started from the beginning and compared 1 and 2. Remember which one that was? The denominator is growing faster, which means we do have a horizontal asymptote at y equals 0. So you're welcome to memorize one of the 3 rules and see which one applies, memorize all 3 rules and then see which one applies, or you're always welcome to use that trick that we mentioned earlier. So at y equals 0, we have a horizontal asymptote. Now, one thing that I haven't mentioned explicitly, but I probably should make a note of, or you should make a note of rather on your notes, would be that horizontal asymptotes, like this one, y equals 0, they can actually be crossed. So it's an idea. It's kind of like a median when you're driving your car. You can cross the median. It's not encouraged, but it can happen. Similarly, my graph can approach a horizontal asymptote. It can touch it and then continue along its merry way. A vertical asymptote, on the other hand, can never be touched because that's a break in the graph with no existence at that input. So make sure you see the difference there. These ones could be crossed, and you can check if that's happening by setting it equal to the function, cross-multiplying, and seeing if you have an x value that's possible. Otherwise, if they're never crossed, that's just fine. Okay, so since we had a horizontal asymptote at 0, remember that guarantees that there is no slant asymptote because they are mutually exclusive. We could also find some points which are actually on the graph by talking intercepts. So for example, to find the x-intercept, I could let y equals 0, and to find the y-intercept, I could let x equals 0. I'll start with the y-intercept. So if you let x equals 0 in the original function, you'd get 0 minus 1 or negative 1 on top. You'd get 0 squared minus 0, which is all 0, minus 2, so negative 2 on the bottom, which is just 1/2. So we now know that our y-intercept is the y value 0.5 or 1/2. So that's somewhere around here. Now that's not a lot of information to go on because we have 3 regions of this graph to check, right? But we have a starting place. What about x-intercepts? Well, if I let y equals 0, the entire thing equals 0, remember for a fraction to equal 0, the numerator has to equal 0. So we could just make x minus 1 equals 0. So x equals, that's right, 1. That's my x-intercept. That's my only x-intercept. That's really helpful to us, believe it or not. What we've just determined by finding that x-intercept at 1, there it is on the graph, we now know the one and only time that we are allowed to cross the x-axis, which also happens to be our horizontal asymptote, so that's okay, that's like the median idea. But we also know that on the left side of this asymptote and the right side of this asymptote and in between, there are no other x-intercepts, so we can't cross anywhere else. So the final question becomes, is my graph to the left of this asymptote, negative 1, is my graph down here or is it up here? Because we know it can't cross the horizontal asymptote anywhere else because that was the x-axis. Now it turns out that if you were to try to get the rest of this graph, what you would need is something called test points, right? And so what I would do is I would pick a point that is to the left of the asymptote, negative 1. So for example, I picked negative 2. And if you plug in negative 2 where? In for x, either in the factored form or in the original. I'll do it one time with you, but then the rest I'll just give you the answers so we can call this problem a day. Okay, we'll finish it up. But for the first one, let's do it together. You would do negative 2 minus 1 over negative 2 squared minus parentheses negative 2 for x minus 2. Now in that situation, look what happens. In your numerator, you get a negative result, a negative 3. In your denominator, you get positive 4 plus 2 rather. So positive 4 plus 2, we're at positive 6, minus 2, so we're at 4. So we end up getting a negative result. We get negative 3 over 4. Now what that means is, at the x value negative 2, which is around here, we're at a negative value. So if this is like negative 1, maybe this is negative 3/4. That's enough information, believe it or not, to draw this sketch in this region. Now we know this graph looks something like this by finding a single point in the region. Similarly, if you test other ones, and I'll just give you the results for you to check on your own, f of 1.5, that would be, for example, if this is x equals 1, 1.5 would be around here. When I put that in my function for x, for that x value, I get negative 0.4. Okay, so when you get that negative value, you know that you are down here somewhere. So this graph appears to be going something like this in this space. Similarly, when I typed in negative half, which is around here, see if you can see that, yeah, f of negative 0.5, if you will, I got positive 1.2. So what I'm really caring about is positivity or negativity. So 1.2 would be around here somewhere. And now this graph is going something like this. It's rising. Finally, the last region to the right of 2, I could pick a test point that's bigger than 2. I picked 3. So for example, f of 3, plugging it in for x, I ended up getting 0.5, positive 0.5. And so at 3, I'm at 0.5, which is enough information, believe it or not, to know that this picture is above the horizontal asymptote. And now I have a sketch which I could compare to my graphing utility, my Desmos, or my TI 83 or 84. Okay, so as you can tell, if you remember from the past when you first studied these types of graphs take a lot of time. You first have to really understand how to get intercepts, asymptotes, and then use test points and symmetry to sketch your rational functions. So make sure you practice because math is not a spectator sport. Good luck. See you next time.